Hi, I'm Fernando Pereira, and today I shall talk about divergence analysis, which is a static analysis used when generating code for GPUs. Most of this class has been taken from a paper called Divergence Analysis, which was published in ACM Toplas in 2013. We shall start the class discussing what are GPUs and why optimizations and analysis are different in this setting. GPUs are the endpoint of a series of evolutions in the design and development of graphics hardware. In the beginning, this hardware was rather simple, the graphics hardware. We had no intelligence at all in the graphics display. The CPU would dump image data into the frame buffer, and the VGA would read it to produce the image. That was quite slow because it took much processing from the CPU. Some graphics functions ended up being implemented in hardware. One of the first of these functions was the rasterizer, which projects a mesh of polygons into a 2D screen. Soon, more functions moved into hardware, and we start talking about the graphics pipeline. That's a sequence of operations that we can apply on images, like resizing, cropping, shadowing, segmenting, and so forth. At that time, some people realized that they could use the graphics pipeline to run programs not really related to image processing. It's like using that very domain-specific hardware to do general-purpose programming. Of course, using this hardware had some advantages. First of all, it was pretty parallel, so soon there were programming languages to use it, and some hardware vendors started designing instruction sets for the graphics pipeline. Once branches were added in, we had a Turing-complete hardware, in addition to the CPU. That eventually became what today we call a GPU, a graphics processing unit, which is a processor specialized in image processing that runs outside the CPU. What's fun is that now GPUs start having specialized hardware on their own. It's like, I have seen that before. The story of GPUs has gone through much progress in the first decade of the 2000s. Here I'm putting some key points to you. Our story, in particular, starts in 2006 with C4 Cuda. I will call it simply Cuda for short. That's a programming language that's good for programming SIMD hardware. And what's an SIMD hardware? We can imagine it as a number of processors that share a single instruction fetcher. We can fetch one instruction and then forward it to all the processors. So these processors must run the same instruction each cycle, but they operate on different data, and from there comes the name. SIMD stands for Single Instruction Multiple Data. That's a bit like a firing squadron. We have the captain issuing orders, and the soldiers obey. Each soldier uses a different gun, but they process the same orders. Today, GPUs can be programmed through a variety of means. The most common programming languages are still Cuda and OpenCL. These languages describe programs that will run in parallel. As an example, let's see how this program looks like when written in C4 Cuda. If you want, you can stop the video and take a look into the program. Try to figure out what the program is doing. Now, down in the figure is the same program, this time in Cuda. Notice that the loop has disappeared. Now what happens is that each thread takes charge of one iteration of the loop. So each thread has a set of identifiers. We use these identifiers to assign threads to different iterations of the loop. And in black you can see the code that invokes the kernel. We call kernel these programs that run in the GPU. Here the kernel is in blue. A GPU has many threads. These threads are grouped in larger units. One of these units is called a warp. A warp, in NVIDIA's jargon, is a set of threads that run in lockstep. They always execute the same instruction together. Cuda programs are embedded in a host programming language, usually C or C++. So on the right, you can see an entire program formed by Cuda in blue and C in red. In NVIDIA's case, these programs are compiled to an intermediate representation called PDX. PDX is like an assembly to describe parallel programs. It contains special registers to identify threads and instructions to synchronize them, for instance. So that concludes our brief explanation of what is a GPU and how they are programmed. In the next class, we start talking about divergences. That's a phenomenon that's very important in this setting.